The second part of Chapter 6 is actually going to deal with climate, and of course climate as compared to weather is a much more long-term factor. It can go anywhere from years to multiple years to decades, even to century in some cases. And there's two main factors that you're going to see in a chart in a second that really come into play with climate. One of them is temperature, and one of them is precipitation. So that is really what drives it. Looking ahead, that's actually what's going to drive the homes too. So here's a really nice organizational chart. If you take a look at the top, of course, climate is the average weather pattern for an area over a long period of time, anywhere from 30 to 1 million years. It's determined by, of course, those two factors, average precipitation and, of course, average temperature. A lot of variables can come into play, and of course forecasting what our temperature is going to be and what our climate is going to be long term is a real difficult thing to do because there's so many variables that come into play. One of which is latitude, how far away from the equatorial regions. Generally, of course, the further you get away from the equatorial region toward the poles, the cooler it's going to be. Altitude comes into play. If you're in a mountain, obviously the higher up you go, the cooler it's going to go too. And ocean currents is another factor. If you take a nation like Britain, Britain is actually warmer because there's warm ocean currents that circulate up all the way from the equatorial regions. Also, Seattle is this way too. Seattle, of course, which is the same latitude as us, more or less has a much warmer climate. They don't get much snow at all. Their winters are about 40 degrees or so, and that's because the ocean currents come into play. So what does this do? It really drives where people are going to live, how people live, of course, what they can grow there, all their basic necessities, whether they can get them or not. So why do climates occur? There's really three main variables, which we're going to break down further in a second. The first one is the amount of incoming solar energy per unit of land. In other words, that is how directly the sun hits where you live. If you look at the diagram at the bottom, of course, it is a picture of the globe at a perfect 90-degree angle up and down and straight up and down, where the sun's rays would definitely hit the equatorial region most directly. Air circulation over the earth, surface of the earth, and water circulation, again, factors we're going to do right now. So major factors determining global air circulation. Number one, uneven heating of the Earth's surface. What happens is, so with this uneven heating of the surface, the equator is what is going to get the most direct sunlight year-round, and of course, what happens is with this uneven heating, it's going to eventually set up a convection current. So if we draw kind of a picture of the Earth like this, and we have the sun hitting the equatorial regions, what's going to happen, of course, is the sun is going to hit that, and as you remember from chemistry or physics, warm air molecules are going to rise. So these things are going to rise up, and eventually they're going to circulate because the Earth is rotating. So what's going to happen are those warm air molecules are going to go up, and they're eventually going to go north, in this case, cool and descend, setting up these convection currents. Same thing's going to happen in the southern hemisphere where the warm molecules are going to go up, they're going to cool and create these convection currents that are going down. And of course we have that very uneven distribution of the sun. The tilt of the Earth is going to change. We see that big time around this region. Think about in the spring and fall. If you're driving eastbound on Highway 94 or even Blue Mound Road, the sun is at an angle where it is really hard to see, and of course traffic gets to be a nightmare because of that. But of course the Earth does tilt according to seasons. Remember, during the spring season, what happens is we're tilting back toward the sun. So what happens is it's hitting us more direct, so it's warmer here. And of course in fall, we're angling away from the sun. So the sun is a little bit more, or less rather, direct, creating a lot less warm temperatures. So the 6 months a year, remember, the poles are either in sunlight or darkness. That's the extreme end of this tilting of the Earth. What happens is in the winter time in the northern hemisphere, and you've got to realize this is a northern hemisphere versus southern hemisphere thing. In the northern hemisphere, at our extreme in the winter, like on December 21st, the poles actually see the North Pole, where Santa lives, of course, they actually see no daylight because they're completely shed from the sun. And the opposite is going to happen in the southern hemisphere, where they're actually going to have 24 hours of daylight. And then, of course, that reverses. Keep in mind, remember that when the northern hemisphere is in summer, the southern hemisphere is in winter. Rotation of the Earth is a huge factor determining global air circulation also, aka winds. Rotation of the Earth on its axis, of course, we're constantly spinning. The air masses actually are faster at the equator than they are at the poles, and what this does is it drives prevailing winds or surface winds too, like the convection currents that I talked about before. Another factor that's going to come into play with wind is actually properties of air, water, land. What happens is water evaporation sets up these cyclical convection currents. So in the equatorial region where it's really hot, we have a very high amount of evaporation. Those water molecules, of course, go up in the atmosphere, cool and fall, and add to our convection currents. Also in the oceans itself, we have convection currents that occur, which we're going to talk about in a little bit when we talk about El Nino, La Nina, and things that affect that. And those will actually drive those global convection currents. They occur both vertically and from place to place in the troposphere. So what happens is, as I said, warm molecules go up, that's the vertical, they cool and they fall back down, thus setting up our wind pattern. Take a look at this little chart right here. Just talks about low pressure system and high pressure system. Of course, a high pressure system is when there's lots of molecules. Sorry about that bell. A high pressure system right here is when we have a lot of warm, dry air that's descending and cooling as it goes, puts a lot of pressure on our Earth. And a low pressure system is when we have less molecules, and what we tend to get is air that is rising. And of course, as it rises, it tends to produce condensation and we get precipitation, convection current. Here's one example of wind right here. This is actually in California. Those were forest fires that occurred a couple of years ago. You can actually see this global picture where these the smoke and everything is getting up into the atmosphere, and eventually that's going to catch the jet streams and drive this way. This also happened similar a couple of years ago in Wisconsin. This region, there were actually wildfires in Minnesota, believe it or not, and the winds were actually blowing it all the way here, so the wind was greatly. Another picture, this is the Sahara Desert. This right here is Spain, and of course Africa right here, so the Sahara Desert in this region. And you can actually see, due to the wind pattern, that the sand is actually going out over the ocean, and of course that's going to affect any islands or any other nations that are close. Three types of convection currents that occur, and this is the same in the northern and the southern hemisphere. The first one is between 0 and 30 degrees north, or 0 and 30 degrees south for that matter, as we get something called the Hadley cells, which I'll talk about in a little bit. Between 30 degrees and 60 degrees north and south, we get something called Ferrel cells, and then finally north of 60 degrees we get something called polar cells, and of course that occurs down in this region too. Polar cells should make, because that's the polar region. So if you think about it, back in the day when ships used to come over from Europe, or we used to transport things back to Europe, the ships really would come into play and need that wind because they use sailing power, and they really took advantage of it. So the Hadley cells, of course, between 0 and 30 degrees. In this region, it creates a lot of different biomes. We can get things like temperate deciduous forests. And then about 30 degrees north latitude and 30 degrees south latitude, what's really interesting is we tend to get kind of a deadened zone, so we don't get a lot of wind patterns there because that's where the convection currents are being made, and we get a lot of deserts being made in that area. But these convection cells are important because it redistributes warm and cold air. It very much can influence vegetation and ultimately biomes. It can help mix ocean nutrients. We're going to talk about that with El Nino. And it really comes into play with our base of our food chain, which is phytoplankton, zooplankton, and fish. So here's another way of looking at these cells and the winds that are going to drive. We've got, of course, the Hadley cells right here. Ferrel cells would be here, and, of course, polar cells right here. We in the United States get what's called westerlies. Again, sorry for the bell. Westerlies are actually our jet stream and the winds coming into play. Our winds come from the west. That's why they're called westerlies. Like I talked about in the last lecture series, is we have weather patterns that are very similar to Iowa and Madison. And what's happening is it's the winds that are blowing in that direction. When you see clouds in southern Wisconsin like this, you can actually see them coming from the west, and that's what is driving our warm fronts and cold fronts pushing this way. Now what's really interesting is we get in the southern region like this, or in the between the 0 and 30 degrees north latitude is trade winds are actually opposite. So if you go to the Caribbean sometime or Hawaii or something like that, winds are actually going to come out of the east. So they come from the northeast. They're called northeast trade winds. Back in the day when they would actually come from Europe to the United States, they would actually have to come all the way down here and catch those trade winds and then go back up to wherever they needed to in the United States. And then on the way back, it was a much shorter trip. They would just follow those westerlies back into that. So wind, of course, moves as a result of unequal heating of the Earth's atmosphere. The trade winds are between 30 degrees latitude and the equator. Northeast trade winds blow from the northeast. The southeast trade winds blow from the southeast. You're not going to have to know exactly where those are, but be familiar with them. As I mentioned before, what really comes into play with us in the United States and what you need to know is, again, sorry for those bells, what you need to know for this class are the westerlies. They're between 30 and 60 degrees latitude, which occupies most of the United States. And our winds, of course, come from the west, which drives our weather pattern atmosphere. Polar easterlies are actually between 60 degrees and the poles. They blow from the north and the east in the northern hemisphere and the south and the east in the southern hemisphere. Don't really need to know a lot about that, but just realize things reverse. Realize that we have the westerlies right here. Things are reversed below us between 0 and 30 degrees, and of course they're reversed above us between 60 degrees and 90 degrees. That should get you what you need to know as far as winds. Winds are very unpredictable, unfortunately, because of different solar patterns and because of different clouds and a lot of different variances like altitude, latitude. There is an area called the horse latitudes between 30 and 35 degrees south latitude. This is an area where early people avoided taking their sailing ships because what happens is this is where convection currents go up. There's actually no wind. So what happened, they're called the horse latitudes because if boaters got stuck in this, they would actually have to throw their horses overboard so they could move on. There's another area called the doldrums, which is near the equatorial region, 5 degrees north, 5 degrees south, again where air rises, and there's no wind there either. So right around the equatorial region, the top and the bottom, it's very calm. Let's stop there and we'll continue on with ocean currents next.